classroom. Your classroom is in AB2, 7th floor. Okay. So till now we have completed one important portion of or one important mode of heat transfer. What we have seen is conduction. We have seen one-dimensional conduction, two-dimensional conduction. What we have not seen is a three-dimensional conduction, but the concepts of two-dimensional conduction, especially the numerical methods, can be extended to three-dimensional conduction also. Similarly, we have seen the case of steady state with heat generation and without heat generation. Similarly, we can also extend those concepts to transient with heat generation and without heat generation. But what we have seen is a transient conduction in one dimension only, and that too without heat generation. Okay. So you learned how to predict the temperature after a certain time, what will be the amount of heat transferred in a given amount of time, so on and so forth. Now, conduction, even though it has taken quite a while, conduction is simple compared to convection, and it's very simple compared to radiation. So just understand that radiation is the most difficult form of heat transfer, mode of heat transfer. From the phenomenon itself, conduction you can actually visualize, and many ways you are familiar with the conduction heat transfer from the real life. But radiation heat transfer, you may be inadvertently familiar with the radiation heat transfer concepts, but visualizing them and expressing them in the form of equations and analyzing and evaluating the equations is difficult, especially because radiation heat transfer is a non-linear form of heat transfer. You remember that in the rate equation for radiation, there is the temperature raised to the power 4. That is the one which brings in a lot of complexity. So whenever you have this radiation heat transfer and the boundary condition is radiation heat transfer, then things become complicated. And then there are many other things in radiation heat transfer. For example, there is something called as a participating medium. So in a radiation heat transfer environment, if the media is vacuum, the amount of radiation is extremely high. And if there is some, if instead of vacuum, we have some media participating in the heat transfer, then it will influence the radiation heat transfer. So a lot of complexities will be brought about, which we shall see. Some of them only we'll see the later modules related to radiation. But as of now, we will take up convection. So conduction is the simplest, radiation is the most difficult, and convection is somewhere in between. So convection heat transfer is mostly related to or the 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 parameter that is mostly enigmatic, that is not known to us, is the heat transfer coefficient. And I've been telling you since the beginning that unlike the thermal conductivity that we came across in heat conduction, the heat transfer coefficient is not a material property. So it varies depending on the situation, depending on the orientation, depending on the fluid that is being used, and depending on the way it is the convection takes place, whether it is a forced convection or natural convection. So first we'll start with the simplest one, which is the forced convection, and we shall see how to evaluate. See, the entire problem of heat convection, see, evaluating the rate of heat transfer is simple. The Newton's law of cooling gives it Q is equal to HA delta T. That's quite simple. What is complicated in radiation heat transfer is estimating the value of the heat transfer coefficient. What is H? Determining H is one of the most difficult tasks involved in the convection heat transfer. So that will be what we'll be seeing in forced convection and later on in free convection also. In forced convection, your syllabus is divided into two major parts. One is external flow and another one is internal flow. External flow is where the fluid flows over some surfaces, and internal flow is where the fluid flows inside pipes or ducts. And another application or extension of the external flow is flow over tube bundles. So you will see that tube bundles are to be expected, are often found in heat exchangers, especially the shell and tube heat exchangers, which we'll see in the module number 7. So in that module, you will also see how to estimate the heat transfer coefficients and how to estimate the heat transfer coefficient on the outside of the tubes. You will learn in this particular module. So this is the content of what we are going to see in this particular module of forced convection. So I'll share my slides now. Now this is called as a convection 1, which involves what is called as the forced convection. Module number 5 is the convection part 2, which deals with the natural convection. So the equations that we are going to see in forced convection and natural convection will be different. All right. Convection heat transfer, some of the concepts these are you are familiar with, but we shall go through the general introduction here. Convective heat transfer occurs wherever there is a fluid moving and thermal gradients exist. So fluid movement is mandatory in convective heat transfer. The fluid movement can be vertical, can be horizontal, can be inclined. The movement can be against a surface. The movement can be against another fluid, so on and so forth. So any fluid movement is convection. And if there is a thermal gradient also involved, we will have convective heat transfer. The convective heat transfer can occur in two modes. One is the forced and other one is the free convection mode. Free convection mode is also called as the natural convection mode. So in this free convection mode, there won't be any external device that can force the fluid to flow. So you won't find any pump or a blower or a fan or a compressor to force the fluid to flow in a free convection mode. Whereas in the forced convection mode, you will have such a external device. A major problem in the study of convective heat transfer is to determine the heat transfer coefficient. The heat transfer coefficient, which has the symbol H, that is the one which poses the maximum amount of problem in the convective heat transfer coefficient because it is not known. And unfortunately, it is not a material property. Therefore, this heat transfer coefficient has to be determined for each and every situation. You have some experience in determining this heat transfer coefficient. In the lab, you have done this experiment on convective heat transfer. One experiment on natural convection, followed by another experiment on forced convection. So in these two studies, what we have done is experimentally determine the value of the heat transfer coefficient. Okay. And there is also a third experiment called as the pin-fin experiment. Maybe some of you have already done it. In that experiment also, we have these two modes of natural convection and forced convection. There we will determine the heat transfer coefficient using the experimental method and also using what are known as heat transfer correlations. So what are these correlations? You will see very soon. So for convective heat transfer, you have seen that there is a fluid movement involved and there is a thermal gradients involved. Whenever there is a fluid movement involved, there is a mass flow, there is a material flow, there is a energy flow because of the thermal gradients involved. And because fluid is involved and fluid has certain mass, there is also momentum transfer involved. So there is a mass transfer or mass flow, momentum transfer, and heat transfer involved in convective heat transfer. So for this, a fair understanding of fluid mechanics is necessary to study convective heat transfer. So until now, in the convection, there was no fluid involved. Inside, at least inside the solid object, there is no fluid involved. Therefore, we didn't bring any concepts of fluid mechanics. But now we'll have to bring the concepts of fluid mechanics. Therefore, understanding of fluid mechanics is necessary for convective heat transfer studies. So I'll show a few concepts that you are already familiar with, that you have already seen in your course on fluid mechanics. One equation or one concept that you have seen is the conservation of mass. So we all know that mass is conserved. Mass can neither be created nor destroyed. So whatever mass goes in must come out under steady flow conditions. Okay, that is what is called as the conservation of mass. Similarly, we have energy conservation and momentum conservation equations. We shall see them. So in the compressible flow mode, you can see here there is an object or a control volume through which a mass enters and the mass leaves this is in the x direction. Similarly, if we are talking about a two-dimensional object, a two-dimensional control volume, there's a mass entering in the y direction and mass leaving in the y direction. So the total net mass entering will be in the x direction will be this quantity minus this quantity. Similarly, net mass entering in the y direction will be this quantity minus this quantity. So when you subtract rho u from this quantity, the only thing that remains is dou by dou x of rho u dx. Similarly, when you subtract rho v from this, you will have dou by dou y of rho v dy. Okay, so on simplifying this and applying the conservation of mass equation, that means total mass entering should be the same as the mass leaving, then we will get what this conservation of mass equation in this form, dou by dou x of rho u plus dou by dou y of rho v. Okay, that is equal to 0. That means derivative of this term rho u in the x direction and derivative of this term rho v in the y direction is equal to 0. Now, if you look at this or just leave this, are you familiar with the continuity equation from fluid mechanics? You heard this word continuity equation, no? In fluid mechanics.
Yes, sir. So volume, I think, will be constant.
What is the form of that equation? Can you tell?
So
QA equal to constant.
Repeat louder.
QA equal to constant.
What is constant? Rho AV. Density, area, velocity. The product of that is supposed to be constant in a compressible flow. In an incompressible flow, density is same. Therefore, AV is constant. Or if you apply this equation to inlet 1 and outlet 2, we will write it as rho 1 A1 V1 is equal to rho 2 A2 V2 for a compressible flow, or incompressible flow, we'll write it as a A1 V1 is equal to A2 V2. So that is the simplest form, especially in a one-dimensional flow. Okay, so here we are talking about two-dimensional flow. The same conservation of mass is nothing but the continuity equation. So this basically what you're seeing here is the continuity equation in 2 dimensions. And in 1 dimension, what happens? This term will vanish, and if it is incompressible flow, density also will be a constant, will come out of the brackets, and what simply remains is dou u by dou x is equal to 0. This is this equation is the differential form of the continuity equation A1 V1 is equal to 0. Or A1 V1 is equal to A2 V2. That's the continuity equation that you are familiar with in fluid mechanics. This equation that you see is its a differential form. Okay, so basically you see here the term inside the brackets, density multiplied by the velocity. You multiply this with area, rho UA. That means the mass in the x direction. Rate of change of mass in the x direction plus rate of change of the mass in the y direction together should be equal to 0. That is the compressible flow equation. That is the conservation of mass equation or the continuity equation for the compressible flow. For the incompressible flow, density remains constant. Therefore, density here and here will come out of the brackets and go to the right-hand side and vanish. And therefore, the incompressible flow equation will be much simpler. Dou u by dou x plus dou v by dou y is equal to 0. And if it is a one dimension only, then this will be du by dx is equal to 0. Instead of dou, we'll write it as a d. Okay, that's the continuity equation. Then we also have the conservation of momentum equation. So you see here, in other words, conservation of momentum equation is also called as the Navier-Stokes equation. And the Navier-Stokes equation written in x, y, and z directions is written here. So basically, you see here, there are several terms which can be grouped. For example, this rho multiplied by dou u by dou t plus u dou u by dou x, v dou u by dou y plus w dou u by dou z. So this is what is called as the acceleration term, the one in the brackets. And this together multiplied by rho will amount to the momentum. Okay, or the force because of the momentum. Rate of change of momentum is force. Now you see here on the right hand side, we also have some terms which dou p by dou x is the pressure term and rho g is the body force and this one is the viscous force. Viscosity is here, this is the viscous force. So viscous forces are dominant in some types of forces. In such cases, we will have to consider this. So this is the viscous forces. Therefore, you can see that the conservation of momentum is basically some kind of a force balance. Okay. So rate of change of momentum is equal to sum of certain forces. So similarly in the y direction and in the z direction. And energy also comes into picture when we talk about heat transfer. Whenever there are temperature gradients, there will be energy also. So you can see there is a control volume taken and there is some energy flow. E dot COND stands for energy transfer in the due to conduction. And E dot ADV, advection. ADV stands for advection. Advection is another word for convection. You have learned about advection here. See this term is the term that is responsible for this advection, flow of the fluid. So this energy advected into this control volume. So energy conducted and energy convected in the x direction is balanced is in this equation. Similarly, energy conducted and convected in the y direction. So all these things, if you put together, sum them, and the net energy conducted in the x direction and y direction, the total sum should be equal to 0. That's where we say the energy conservation is taking place, or the energy is conserved. So when we write that equation and put all of the terms in perspective, you will have energy convected should be equal to the energy convected minus some term taking care of the energy conversion between the mechanical and thermal. For example, if there is any friction, then there will be a generation of heat, and that is taken care here. Similarly, viscous dissipation. Again, viscous dissipation, whenever viscosity is there, it resists the flow of flow of the fluid, and that can become some kind of a form of energy, and that is called as the viscous dissipation. And this again is a large term, therefore it is written separately. Viscous dissipation is written as a mu phi, and this mu phi is elaborated here, and there is one heat generation term. So all this put together, you see here, energy conducted and convected plus heat generated and energy conducted and convected out in the x direction. Similarly, in the y direction, if you write all these things together and say that the energy is conserved, that means there is no energy storage taking place, then you get this equation. So basically, this is the steady state energy conservation equation in 2 dimensions. Now you can imagine if there is the 3rd dimension, it will become a little more complicated also. So all these 3 laws, conservation of momentum, conservation of mass, conservation of energy, all these 3 will play a major role in the convective heat transfer. Now you can see that all these equations are partial differential equations. So partial differential equations, there are many unknowns also. For example, there is the temperature not known, there is a velocities may not be known, and so on. Therefore, there will be several unknowns for which if you want to solve, you will have to apply certain boundary conditions. So solving these partial differential equations with the relevant boundary conditions will become what is called as a problem of computational fluid dynamics. And for this also, there are ways of dealing. There is a analytical method and there are popular numerical methods. Okay, so this is what is involved in convective heat transfer. Energy conservation, mass conservation, and momentum conservation is involved, and that we will apply whenever there is the need. So these conservation equations are basically solved using either techniques of mathematics, or for that is possible only for simple cases, and for complex cases we use software packages like Fluent. Okay, now let us look at some other concepts that we are already familiar. There is some concept called as the boundary layer. We have seen this word or come across this word boundary layer in what we call what is that in fluid mechanics. The boundary layer is a thin layer in which fluid velocity gradients and the shear stresses are large. So you see here, it's basically a thin fluid layer in the order of microns or millimeters. So it's a very thin layer, and inside that layer there will be certain velocity gradients, and these velocity gradients will bring about shear stresses. Okay, so outside the boundary layer, the velocity gradients and shear stresses are negligible. So you can see here is a schematic. There is a flat plate with a sharp edge, and over this flat plate, certain fluid is flowing. So this arrangement can be made very simply by putting a table fan. So here you locate a table fan and switch it on. Air flows over this table or over this bench, and or this is called as the flat plate. So over this, you can see this is the fluid profile, velocity profile, just before it strikes the table. But once it strikes the table, what happens? Because of the no slip condition, the velocity at the surface of the table will become zero because the table is stationary. And over as you move away from the surface of the table, the velocity should reach the value u infinity. U infinity is called as the free stream velocity. This is the name, free stream velocity. So from a point of zero velocity to a point of a free stream velocity, the velocity changes takes place. So as the velocity changes are taking place, uh, we see these velocity changes or velocity variations inside this region called as the boundary layer. So when velocities are changing, we call it as a velocity boundary layer. Okay. And this velocity boundary layer, you can see there is a velocity gradient across this thickness, and therefore this velocity gradient across this thickness will be responsible for bringing in shear stresses. You are familiar with the concept of the shear stress. Shear stress is mu du by dy. You have seen that in fluid mechanics. So that comes into picture and that brings in shear stresses. Therefore, wherever there are velocity gradients, you will have these shear stresses. Now, there is this concept of boundary layer thickness. So what is this boundary layer thickness? So it is the thickness where the velocity is equal to 0.99 times the free stream velocity or 99% of the free stream velocity. Okay. Therefore, you can see here at the point on the table or on the plate, the free stream, the velocity is zero because of the no slip condition. But as you move up, the velocity increases. You can also see the length of this arrow keeps increasing as you move up. So the velocity is increasing as you move in the y direction, and at one point, at this point, the velocity will be equal to 99% of the free stream velocity. So that thickness, that point where the velocity is equal to 99% of the free stream velocity is called as the boundary layer thickness. Now you can see that here the boundary layer thickness is small, but as you move along the x direction, the boundary layer thickness is increasing. Okay, so the boundary layer thickness is basically a function of the plate length. So as you move along the direction of the plate length, the boundary layer thickness keeps increasing. And that means you can see velocity variations inside this boundary layer, but these velocity variations are kind of becoming flat because the height is increasing. Therefore, in the initial regions, when the distance is close to x is equal to 0, that means in this region, the velocity gradients are quite steep. Whereas as you move away from the edge of the plate, as you move away, come to this region, the velocity gradients will become kind of a flat. Now, in the velocity boundary layer, there are certain things called as the friction coefficient. We have seen that these velocity gradients will bring about shear stresses, and these shear stresses act in the direction against the flow. So these shear stresses are kind of a resistance force to the flow, and they offer certain friction. That friction coefficient is defined as CF. C coefficient F for friction, that is equal to tau S. Tau S is the shear stress divided by rho u square by 2. Okay, this is how the friction coefficient is defined. This is a non-dimensional quantity, and you can see the definition of this, the same equation you can see in your data book, page number 121. So all of you open your page number 121, and you will be able to see the equation for friction coefficient. On the notation side, on the last column, CFX is a local friction coefficient defined by tau Wx divided by rho u square by 2. The same equation. And we also know that the shear stress is a mu du by dy. So the shear stress is proportional to the velocity gradient, or shear stress is proportional to what is this viscosity. Okay, so this kind of a relation is obtained, and this kind of a relation is useful for us to determine what will be the amount of pumping power. So how much power is needed to blow air across the surface of the table, because the surface of the table is offering certain resistance based on the friction coefficient, and therefore we will know how much will be the fan power and so on. Then we come to what is called as the thermal boundary layer thickness. Just like a velocity boundary layer thickness, the thermal boundary layer thickness also is defined. So in velocity boundary layer, we have seen that inside the boundary layer, there are velocity gradients. Likewise, in the thermal boundary layer, we will see that there are thermal gradients. So you can see here, there is a plate which is having a temperature Ts. And over this plate, there is a fluid flowing with a temperature T infinity, and the fluid flow velocity is a U infinity. U infinity is the free stream velocity, and this fluid has got a temperature T infinity. And when this fluid strikes the edge of the plate, this is the temperature profile. You can see it is quite uniform. But as it flows over the plate, what happens? There is a heat transfer taking place between the plate surface and the fluid, because of which there will be thermal gradient. You can see at this point of contact between the fluid and the plate, the first layer that is in touch with the fluid and the plate, we will have conduction heat transfer. And from the layer, from that first layer to the subsequent layers above, we will have convective heat transfer. So in this region, conduction takes place, and above that, convection takes place. But because of this heat transfers due to conduction and convection, we will have thermal gradients. So what happens? Let us assume that in this particular case, the surface temperature of the plate is higher than the fluid temperature. That means we are dealing with a hot plate. Over a hot plate, some cold fluid is flowing. So what happens if at some location of X distance from the edge of the plate, if we measure the temperatures in the fluid, the bottommost layer of the fluid will be hotter. And as you move upwards, the temperature of the fluid keeps decreasing. And at some point, the temperature will be equal to the free stream temperature. So you can see here, the magnitudes of the temperature is determined by the length of this line. The bottommost line is longer, and as you go up, the length of the line is becoming shorter, shorter, and at the top, it becomes the shortest. So at the top, the line indicates that the length of the line is an indicator of this magnitude of temperature T infinity, and at the bottom, the length of the line indicates the magnitude of the surface temperature Ts. So the temperature gradient is changing from Ts to T infinity. So there is a gradual change in the temperatures, and the thermal boundary layer thickness is defined as that thickness. It is represented as delta T at thickness where thickness equal to Y, because it's in the Y direction, where this temperature difference ratio is equal to 0.99. What is this temperature difference ratio? Ts minus T. Ts, surface temperature, minus the temperature of the fluid, divided by Ts minus T infinity. That is the initial temperature difference or the maximum temperature difference possible. This ratio equals to 0.99 or 99%. You see here, this 99% that number has repeated once again. So once for the velocity boundary layer and once for the thermal boundary layer. So this 99% is a measure of the temperature attained. Okay, so this temperature difference ratio, when it reduces or when it attains this 99%, that thickness is called as the thermal boundary layer thickness. This is delta T is called as the thermal boundary layer, and this delta is called as the velocity boundary layer, or in some cases, it's also called as the hydrodynamic boundary layer. Sometimes the symbol is not simply delta, it can also be delta with a subscript H. So remember this velocity boundary layer, there will be velocity gradients, and in thermal boundary layer, there will be thermal gradients. Because of the velocity boundary layer, there will be shear stresses possible, and because of the thermal boundary layer, there are thermal gradients possible, and because of the thermal gradients, there will be heat transfer taking place. And since the thermal gradients are quite steep inside the boundary layer, the heat transfer is maximum inside the boundary layer, and outside the boundary layer, the amount of heat transfer is negligible. Okay, that is the significance of this boundary layer thicknesses. Now you see here, if at this interface between the plate and the fluid, if you take a control volume and apply an energy balance, what is happening? There is heat conduction taking place from the plate to the fluid, and from the fluid, the heat is convected away. into the adjacent layers of the fluid. So there is a heat conducted which is convected away. So in this region, if you take a control volume and apply the energy balance, you can see the heat flux at the surface is heat conducted minus K dou T by dou Y. Minus K. K is the conductivity and K is the conductivity of the fluid at the lowermost layer, dou T by dou Y. Why we have taken the conductivity of the fluid and not the conductivity of the plate? Because we are dealing with the convection inside this boundary layer. We are not dealing with the conduction inside the plate. At the interface, what is happening? That's what we are talking about. And moreover, the layer that is attached to the plate is stationary. It is not moving. Therefore, it behaves as if it's a solid. So conductivity of the fluid multiplied by the thermal gradient at this interface is equal to the heat convected away. This is a H A delta T, but with A removed. So the A has been taken to the left hand side. So this heat has become heat flux. So conduction heat flux is equal to the convection heat flux. So from this, we can evaluate the value of the heat transfer coefficient in this particular experiment. Okay, so you see here how to evaluate the heat transfer coefficient. We should know the thermal conductivity of the fluid, which can be known because it's a material property. We should be able to measure the thermal gradients here. Dou T by dou Y at Y is equal to 0. That means at the plate surface, we should be able to measure the temperature variations with respect to height. So that means determining this value dou T by dou Y will involve some kind of a plotting of the temperature along the Y direction. And in the denominator, you see there is a Ts minus T infinity. Ts is the surface temperature, T infinity is the free stream temperature. That means we will need some temperature measurement. So measuring the temperature, knowing the conductivity of the fluid, and measuring the height is necessary to determine the heat transfer coefficient. So this is one way of determining the heat transfer coefficient. You have done experiment like natural convection and forced convection heat transfer coefficient, where what you did is you measured the surface temperatures and equated that to the amount of heat generated using the electrical power supply. Okay, so by using that and using the Newton's law of cooling, you are able to determine the heat transfer coefficient. So this is very much similar, except that instead of this heat generated by electrical heaters, here we are using the heat convected away at the interface. So this is the method used to determine the heat transfer in convection. So we have some inferences from the thermal boundary layer. Conditions in the thermal boundary, TBL is the short form of thermal boundary layer. Conditions in the thermal boundary layer influence the wall thermal gradient. Okay, so whatever happens in this thermal boundary layer is influencing the wall thermal gradient, the thermal gradient at the wall. Now, just one important point is, you see, we are talking here about the thermal boundary layer. It is basically a thickness in the y direction. Similarly, here we spoke about the velocity boundary layer, which is also some kind of a thickness in the y direction. Now, will the thermal boundary layer and the velocity boundary layer be same for a fluid flowing over a hot plate? In some cases it can be, but in most cases it is different. Thermal boundary layer can be higher than the velocity boundary layer or can be lesser than the velocity boundary layer. So that depends on other parameter, which we shall see later. So inside the thermal boundary layer, as X increases, delta T increases. Delta T is the thermal boundary layer thickness. So as X increases, that means as we move towards the right, the thickness of the thermal boundary layer increases. We have observed the same in the case of the velocity boundary layer also. Thermal gradients decrease. This also we have seen. So initially in this region, since the distance is very small, the thermal gradients are high. But as you move away from the edge, that means as X increases, the thermal boundary layer distance is large, the thickness is large, and therefore the thermal gradients will decrease. Heat flux decreases. Heat flux decreases. That means as you go away from the edge, as you move in the X direction, the amount of heat flux and thereby the amount of heat transferred also will decrease. That means most of the heat is transferred in this region, whereas the amount of heat transferred in this region is becoming lesser and lesser. And heat transfer coefficient decreases. So as because of the heat flux is decreasing, heat transfer is decreasing, and therefore heat transfer coefficient also decreases. That means the heat transfer coefficient is maximum in this region, whereas the heat transfer coefficient decreases as you go in this x direction. That means if you try to plot the heat transfer coefficient in the x direction, it will be a high value here and it will keep on decreasing like this. So these are some points you can remember, or it's important to remember as far as the thermal boundary layer is concerned. Now coming to determining the heat transfer coefficient. So what is this average heat transfer coefficient and a local? There is some word called as the local heat transfer coefficient. Local heat transfer coefficient, average heat transfer coefficient, so on and so forth. So what are these? So just consider an aerofoil shaped surface. Okay, this is a common surface that is encountered in aerodynamics studies, especially the shape of many blades of turbo machines, or the aircraft wing shape also is in this approximately in this shape. This is called as an aerofoil shape, which is known for providing a low amount of drag and high amount of lift. So over this aerodynamic shape, aerofoil shape, there is some fluid flowing. The velocity of the fluid is V. It's at a temperature T infinity, and this shape is flowing. Now, if this object is extremely large, like in the case of a aircraft wing, it has the length itself is a few tens of meters, but the width of the wing will be maybe a couple of meters long. Again, that depends on the size of the aircraft. So this length is very, very large, and therefore if you take a small distance and consider this area, it can be treated as a flat surface. Just like we know that Earth is curved, but for finite distances, we treat it as a flat surface. Likewise, here you see this marked area DAS is now represented here as a flat surface. So through this area DAS, there is some heat flux, Q double prime. This is the heat flux. So there is a fluid flowing at this point. The free stream velocity is U infinity. Remember, the entry velocity is V, but at this point, the velocity can be different. Okay, because of the shape. So at this point, the velocity, free stream velocity is represented as U infinity, and the temperature is T infinity. So at this point, we have these velocities and temperatures, and this is the area we are of interest that is considered ds. Now, if I want to evaluate the heat transfer in this small area, heat transfer is the elemental heat transferred in this area is Q double prime, that's the heat flux in this area, multiplied by the differential amount of area, which is DAS. So Q double prime DAS gives the amount of heat transferred in this differential area. If I want to find out the area on the whole surface AS, then I have to integrate this Q double prime DAS over the entire surface. So we have this integral performed over this surface. Okay, now Q double prime can be written as a H, heat transfer coefficient, multiplied by the difference of the surface temperature and the fluid temperature. So Ts minus T infinity multiplied by H is nothing but Q double prime. Now, if the surface temperature and the fluid temperature are kept constant, the Ts minus T infinity becomes a constant and can come out of the integral. So we have integral of H DAS, this integration performed over the entire surface area. So this Q heat transfer is now simplified as H bar, which is the average heat transfer coefficient multiplied by the area of the surface multiplied by Ts minus T infinity. So this is the general representation. This is the Newton's law of cooling that we are quite familiar with. So this H bar is obtained by averaging the heat transfer coefficient over this entire surface. And this AS is nothing but the integral of DAS. So if you carry out this integration properly over this entire area, then you will end up with this kind of an equation where H bar is the average heat transfer coefficient. So this area average heat transfer coefficient can be written as 1 by AS integral H DAS. So you see, if you equate this and this, you can separate out H bar. H bar is 1 by AS integral H DAS. But to evaluate this integral, you should know how the heat transfer coefficient changes with respect to the area. Or in the case of the flat plate, you should know how this value of H changes with respect to X. So for a flat plate, H varies only with the distance, and therefore the average heat transfer coefficient can be written as, in place of area, we write length 1 by L integral 0 to L H dx. H is as it is. DAS is simplified as a dx because DAS actually length multiplied by the dx, width multiplied by dx. That gives the differential area. So that width is common in area and also this thing. Therefore, it has been ignored, especially for the flat plate. Okay, so this is one way of estimating the average heat transfer coefficient. Now you see here we have H bar and we have H. This H is called as the local heat transfer coefficient. So this local heat transfer coefficient, that means at this point the value is H, but H bar is for the entire plate. We are interested in the average heat transfer coefficients only. We are not generally not interested in the local heat transfer coefficients. Therefore, we should have some ways of estimating the average heat transfer coefficient. So in your experiments also, if you look at the aim of the experiment, you will see that the aim is to determine the average heat transfer coefficient of natural convection in that particular experimental situation. Similarly, average heat transfer coefficient in the forced convection experiment also. So what we are determining is the average value, and that is the most useful one, because you see here in the equation for heat transfer, we have used the average heat transfer coefficient only and not the local heat transfer coefficient. But it will be interesting to know what will be the local heat transfer coefficient. And as mentioned here in this point, the local heat transfer coefficient decreases along the direction of as x. That means as x increases. That means as you go in the x direction, the local heat transfer coefficient keeps decreasing, and it will be maximum here in this region. The local heat transfer coefficient will be maximum, but it will keep decreasing. So we will be interested to know what is the average heat transfer coefficient. So this is how we find the average heat transfer coefficient. Okay, and then we also have what is called as the laminar flow and turbulent flow. We are familiar with laminar and turbulent flows, and we know that the Reynolds number is the non-dimensional number that characterizes or that differentiates between the laminar and the turbulent flows. So here also we have what is called as the local Reynolds number, and we also have the critical Reynolds number. So local Reynolds number is defined as a rho u infinity x divided by mu. That means depending on the value of x, the Reynolds number can be determined. So this Reynolds number is at a particular x. In fluid mechanics, normally we wrote it as a rho v d divided by mu. D is the diameter or the characteristic length. So in fluid mechanics, we generally used it in pipe flows where the characteristic dimension is the diameter. But the general formula for Reynolds number is rho v x by mu. You see in this Reynolds number, in the numerator we have velocities and density. Density is indirectly proportional to the mass and velocity. Mass multiplied by the velocity gives you what is called as the momentum. And in the denominator you have viscosity. That means in the numerator we have momentum or inertia force, and in the denominator we have what is called as the viscous forces. So Reynolds number is basically a comparison of the inertia forces and the viscous forces. Whichever is dominant will determine whether the flow is turbulent or laminar. In laminar flows, the viscous forces will be dominant, whereas in turbulent flows, the inertia forces will be dominant. In other words, in turbulent flows, the velocities will be high, whereas in the laminar flows, the velocities will be low. We also have this critical Reynolds number. Now, remember, this critical Reynolds number is a function of the type of the flow. So for flow over surfaces or external flow, or like flat flow over a flat plate, the critical Reynolds number is typically 5 multiplied by 10 power 5. So this is a number worth remembering. So wherever the flow is less than the critical Reynolds number, the flow is laminar, and above that, the flow is either transitional or turbulent. So here you see there is a velocity boundary layer shown, and initially this region is showing laminar flow where the flow regimes are flowing layer by layer, one over other, and the flow is very orderly in nature. Whereas on the extreme side, you can see that the flow is haphazard. You can see these arrows; they are quite random in orientation, whereas in this region, they are quite orderly in nature. So whenever there is orderly prevailing, the flow is considered laminar, and on the other side, the flow is considered turbulent. So in this region, the Reynolds number, if you calculate, it will be less than 5 multiplied by 10 power 5. And in this region, the Reynolds number will be greater than 5 multiplied by 10 power 5. So in between this laminar and turbulent regions, there is a short region where it is called as the transitional region. The flow is changing from laminar to turbulent, and it will take some time or some distance of flow to change from laminar to turbulent. And also, you see the velocity profiles here. In the laminar region, towards the end of the laminar region, you can see that the velocity gradients are quite steep. Whereas in the turbulent region, you see the velocities, this entire region is more or less constant, it's very flat, right? But here it is not so. So here you can see this is kind of a parabolic velocity profile, whereas here it is not parabolic. Only up to this point it's a parabolic, but it's quite a flat parabola. Whereas in this region, it has become more or less flat. So the velocity profiles also change. Because of the changes in the velocity profiles, the amount of shear stresses exerted in this region will be different from the amount of shear stresses that are exerted in this region. So a lot of these things play a role in the heat transfer also. Now we will see some dimensionless numbers before we conclude today's class. You can see here the first one is the Reynolds number, which we are familiar with from fluid mechanics also. So it's a ratio of the inertia forces to the viscous forces. Now, if you refer to page number 120 of your data book, you will see a big list of different dimensionless numbers that are very frequently used in heat transfer. What I have listed, only 4 of these are listed here. These are very commonly used in, we'll come across these 4 non-dimensional numbers in the heat transfer course that you are going to study. So the first one is the Reynolds number, which is a ratio of the inertia and viscous forces. The second one is the Prandtl number, represented as a PR. It is the ratio of the momentum diffusivity to thermal diffusivity. So how quickly a force introduced into a fluid stream propagates in the fluid stream, and how quickly a temperature disturbance or thermal wave introduced into a fluid stream gets diffused into the fluid stream. That is a measure done by what is called as the Prandtl number. Momentum diffusivity and thermal diffusivity. How quickly momentum passes and how quickly the temperature passes. So the ratio of this momentum diffusivity and the thermal diffusivity will determine how quickly the velocity boundary layer is formed and how quickly the thermal boundary layer is formed. So this Prandtl number determines which one is higher, whether the thermal boundary layer is higher or the velocity boundary layer is higher. Similarly, we have another number called as the Nusselt number. It is a ratio of the convection heat transfer to the conduction heat transfer. So it compares between the rate of heat conducted and the rate of heat convected. And Grashof number, this is the one which will come across in natural convection. It is the ratio of the buoyancy forces to the viscous forces. Buoyancy forces are the dominant forces in natural convection. Remember, in natural convection, there are no inertial forces because there is the velocities are so low that inertial forces are negligible. Therefore, we don't consider inertial forces there, but buoyancy, which results because of the temperature differences, which in turn cause density differences, will result in buoyancy, and therefore we have this buoyancy forces. When we compare buoyancy forces to the viscous forces, that particular number is called as the Grashof number. As I told in page number 120, the equations for all these are available. You can refer to that. Anyway, we'll continue in tomorrow's class, and we'll also try to solve any problem that we may have. If time permits, we'll do that in tomorrow's class. Okay. So now let me take your attendance. Give me your attendance. Mrutunidhi. Abhilash.
Present, sir.
Dan Cherian. Madhusudan.
Sir, Mrityunjay present, sir.
Dan Cherian.
Present, sir.
Madhusudan.
Yes, sir.
Pranav Dilip,
Present, sir.
Siddharth,
Present, sir.
Srivatsan,
Present, sir.
Maitreyan,
Present, sir.
Palanivel,
Sir, present, sir.
Prashant,
Yes, sir.
Tamilalagan,
Present, sir.
Niranjan,
Present, sir.
Vaibhav Karan,
Present, sir.
Abhijit Menon, Kritik Krishna, Praveen, Adil Sinju,
Adil present, sir.
Chaturvedi,
Present, sir.
Chintan, Hamza Hassan,
Sir, Chintan present, sir. Sir,
Sir,
Chintan
Hamza.
present.
okay, Ayush Tripathi,
Present, sir.
Harshavardhan,
Present, sir.
Hemant Kumar,
Present, sir.
Vishwa,
Present, sir.
Chandramouli Singh,
Present, sir.
Shubhwania,
Present, sir.
Sai Rohit,
Present, sir.
Sri Raman,
Present, sir.
Vishal,
Present, sir.
Deepesh,
Present, sir.
Anirudh Venkat,
Yes, sir.
Sri Kumaran,
Present, sir.
Sundar Krishna, Pranav,
Yes, sir.
Jayanti,
Present, sir.
Sriniket,
Present, sir. Present, sir.
Badri Narayanan,
Present, sir.
Avito, Ajit,
Present, sir.
Harish Raghav,
Yes, sir.
Rahul,
Present, sir.
Firoz,
Present, sir.
Nihar,
Present, sir.
Vishnu Karthik,
Present, sir.
Gauri Shankar, Motishwar,
Present, sir.
Vijay Prakash,
Yes, sir.
Tuja,
Present, sir.
Prem Kumar,
Yes, sir.
Charan Sarvesh,
Present, sir.
Charan Ajay,
Present, sir.
Benold Simon,
Yes, sir.
Vamsi Krishna, Venkatesh,
Present, sir.
Jnanakshaya,
Present, sir.
Kiran Dev,
Kiran the present, sir.
Varun,
Present, sir.
Kunal Rao,
Kunal present, sir.
Vignesh Krishna,
Present, sir.
Vedant Madhur,
Present, sir.
Vishwanand,
Present, sir.
Shivani,
Present, sir.
Riya Vasan,
Present, sir.
Kalaipriyan,
Present, sir.
Shankar Narayanan,
Present, sir.
Anish,
Present, sir.
Santosh Raj,
Present, sir.
Keshav Kumar,
Present, sir.
Akash Kumar,
Present, sir.
Karthik Prasanna,
Present, sir.
Sai Kaustubh,
Present, sir.
Varun Halyan,
Present, sir.
Sarvesh Krishnan,
Present, sir.
Elsie Femina,
Present, sir.
Jeff at Gionel,
Present, sir.
Amal Manoj,
Present, sir.
all absentees once again. Kritik Krishna, Praveen,
Praveen present, sir.
Sir, in chat box, sir.
who is that? Sundar Krishna,
Present, sir.
Avito,
Present, sir.
Gauri Shankar, Vamsi Krishna,
Present, sir.
All right. So let's meet tomorrow, and if time permits, I will